All right, so today we're talking 4.1 notes, day one. This is going into our brand new module, module 4, in our first section of notes. So I'm going to share my teacher notes with you here. Make sure that we're getting everything we need down. So first thing, this is called apportionment. Um, Basically, we've got. Let's just kind of read through some of the notes that we have, and then I'll highlight as we go on. So, first thing here in our notes, it says that representatives and direct taxes shall be apportioned among the several states, which may be included within this union, according to their respective numbers, which shall be determined by adding to the whole number of free persons. So a proportionment actually is in the United States Constitution in Article 1, Section 2. Now, did you need to know that? No, but what this does is it relates the idea back to history and, you know, going straight into our Constitution. So we're going to talk about, what this is and what we're going to be doing. Now, the first thing, this apportionment problem is going to be dividing or sharing proportionality, like proportions, based on more information than number of players. So, for example, one, we have Mrs. Phillips has 50 identical pieces of chocolate, which she is planning to divide among her 5 children. She wants to do this fairly, so you would immediately think, all right, fair share, what's their values? That's what we've been talking about. But what would be one fair way to divide this chocolate back from chapter 3? Well, there's 5 children, 50 pieces. 50 divided by 5 is going to give you 10 for each child. That should make sense. However, however, this is where you guys get caught up, so don't let it mess you up too much. We're going to teach, or she's going to teach her children a lesson about hard work, and she decides to give her children candy based on how much time they work during chores in the next week. So, proportionality. The more they work, the more chocolate or candy that they get. So, that is called proportionality criterion. So, child number one worked for 150 minutes. Child number two, 78, and here are all of the respective child. So, every child altogether worked for a total of 900 minutes. So we're basing this off of 900. So what we're going to do is we're going to take the number of pieces and take that child's work hours divided by every child's work hours. And that's going to give child number one 8.333. Child number two, again, they worked 78 divided by what everybody worked, which was 900, and then multiply it by the 50 pieces of candy. So you can see where all of this comes into play. Now, each one of these should all add up to be 50, and they do. Okay, how many times or how many minutes of chores would a child need to work to earn, say, maybe one piece of candy? So if they wanted to work after knowing that everybody's going to work for 900 minutes, um, how much would they need to work to earn one piece of candy? Well, we will set up a proportion in this regard. So 900 minutes of chores over 50 pieces would be kind of the total. So what we want to do is kind of say that that's going to equal 18 minutes per one piece of candy. So we set up a proportion. What does this reduce down to? Well, 900 over 50 reduces to 18 over 1. So 18 minutes per one candy. Now, these are how much, so there, she's going to end up having to split this up a little bit. But that's how much every child that she has gets per minutes that they worked. Let's look at another example here. It says Dr. Williams has 60 blank DVDs to give 4 students in each class or in a class. So 60 blank DVDs to give 4 students. So what would be one way to divide the DVDs? Well, one way is just 60 divided by 4, which is 15 DVDs per student. However, Dr. Williams thinks that the DVD should be given to the students based on their last test scores. So, based on what Dr. Williams is thinking, he's taking everybody's test score and adding them up to get the total. Now, the total here is going to be 360. 80 plus 88, or 85 plus 88 plus 92 plus 95 is 360. Now, what he's going to then do is take the total number of DVDs and take that child or that student score divided by the total score. So we will say 60 times 85 over 360, which equals 14.16. 88 divided by 360 times 60, 14.6 repeating, and so on and so forth. So then the question is asked, for how many points earned on the test should a student earn to get one DVD? All we have to do is reduce the fraction. 360 over 60 reduces down to 6 points per one DVD. So if you got 6 points on the test, you would get one DVD. So, based on these examples, are there challenges to share the items proportionally to all the individuals? The fraction and the decimal increment means you can't share whole values, and you may have already recognized this thinking back in part B and part A. Hey, wait a minute, I can't give off 0.16 repeating, of a DVD, or I can't give away 0.3 repeating of a piece of chocolate. Now you probably could, you could cut that one, so that might not have been a big issue, but the DVD is, because then it doesn't work if you cut it. So the problem that we have is that we can't give out these whole values because they're fractions or decimals. So items can't be cut smaller. What we call those are discrete items. If they can't be cut, they're discrete. So a proportionate method will determine what whole number of items that will be given. So now we'll get through like when do we give off that whole number item. So here are elements of proportionment. So we've got states. States are players involved in a proportionment. The states are the players who are involved. Who gets and receives seats? Say we're thinking about seats in maybe a representation, the House of Representatives, things of that nature. So in the notation for n states, a sub 1, a sub 2, all the way to a sub n. Now, seats. This is a set of m identical, or m is just an arbitrary number, identical indivisible objects to be divided. The more seats, the more states. There are going to be more seats than states. This is indivisible. One seat cannot be shared among multiple states. So what is given? We know that our seats must be greater than or equal to the states that we have. The populations. The populations is a set of n positive numbers, n arbitrary number, which are the basis for the apportionment of seats to the state. Proportionality criterion is what we will call this. So how is it given? The additional information for proportionments is what we'll need here. All right, notation for n populations. We're going to take population 1, population 2, population n, like we did back up here in the test scores, and add them all together, and that will give us the total population. Okay, so what we're going to do on 1 through 4 is identify what are the seats, the populations, and the states. So example 1 says Mr. Gate plans to split 3,500 allowances between his 4 children at the end of the quarter. The children will receive their allowances in proportion to their GPA. What are the states? Who are the players? The players are the children. What are the populations? What are we adding together, right, to base this off of? The population would be, in this case, the GPA. And then what are the seats, right? What are they going to get based off of this? An allowance. So the seats are what they get. The states are who they are, who are the players, and the population is what we're basing what they get off of, in this case, their GPA. So for example 2, there are 40 teachers in an elementary school, and the principal plans to apportion teachers to the 5th grade, levels 1 through 5, in the school based on the current enrollment of that grade level. So what are the states? The states are the grade levels. The states are the things that are the players that we have, the grade levels. Okay, what's the population? What are we basing these off of? Well, these are the students in here in this regard. Why are they the students? Because what we get, or the teachers for the state or the grade level, is based on the population of students. Okay. I'm going to let you think about number 3 and number 4. If you have any questions, you can email me there. I'm not going to go through them here, but I think you can get a good idea based on examples 1 and 2. Let's talk about ratios and fractions. We've been struggling with this throughout the semester. So ratios, fractions are the important measurement of a proportionment. So the standard divider, or what we call SD, This is the ratio of total population to seats. So SD equals the total population divided by the seats. So the standard divisor is the population over the seats after we've added everything together. So P over M. This standard divisor represents the number of people, population, per one seat. So how many people do we need for one seat? Then we have these standard quotas, which we'll talk about what they are. So the standard quota, which we'll call Q, is a ratio of state population P to the standard divisor. So the way that we find Q is we take the state population, the state's population, and the standard divisor, and we divide them. So whatever the population for the state is, divided by the standard divisor. So same as in the example P divided by P times M, what we found up above in those first two examples. You can refer back to those if needed. The standard quota, and we have two other quotas which we'll talk about later, but the standard quota represents the exact number, including the decimal, of seats that each state should get. Should is the key word. If one seat could be divided into smaller pieces. Again, could, the key word. Meaning when we find the standard quota, we're going to get a decimal, and sometimes what we're looking for is discrete, or it's non-divisible or divisible. So we need to keep that in mind. Okay, so the total of standard quotas is going to be equal to the seats that we have. Let's take a look at example 3. Example 3 says, consider a nation of 6 states with only 250 seats in their Congress with different populations. So what you see on your blank document, if you're looking at that, is state A, B, C, D, all the way to F, and then we have the population there for each one. Now what we're going to do is we're going to add all of their populations together for each state, and we're going to get 12,500,000. So that's the total population of those 6 states. Now there are only 250 seats in Congress for those states. So we're going to have to figure out how we divvy up those 250 seats to those 6 states, which is what we do in Congress anyway. So the way that we do this is what we're going to, and this might not be exactly how, right, we're using different numbers, but this is how it is done in Congress. So the way that we do this is to find the standard quota. Remember our formula. We're going to take the state population and divide it by the standard divisor. So what we need to find first is what the standard divisor is. The way that we find the standard divisor is the total population divided by seats. So we found our total population in 12,500,000. We divide it by the 250 seats that is allotted to Congress. So 12,500,000 divided by 250 gives us 50,000 as the standard divisor. Now, again, the standard divisor represents the total number of people needed per one seat. So we need 50,000 people to get a seat in Congress here. So this standard quota, we then take the state population, in this population of A, 1,646,000, and divide it by the standard divisor of 50,000. So state population 1,646,000 divided by 50,000 will give us 32.92. We'll do it again for B. 6,936,000 divided by the standard divisor of 50,000 gives us 138.72. C, again, 154,000 divided by 50,000 gives us 3.08. And so these are all of the seats allotted for those 6 states, which should add to a total of 250, or the number of seats allotted. And it does. The problem here is we can't give away 0.92 of a seat. We can't give away 0.8 of a seat. So what are we going to do? Let's try normal rounded, the 0.5 rule. Remember, the 0.5 rule is 1 to 4, round down, 5 or above, round up. So this will go to 33 to 139, down to 3 to 42 to 14 to 20. The problem here is that we have 251. So there are special roundings of quotas where the 0.5 rule does not apply. We can't give away an extra seat because we don't have an extra seat to give away. So we have the upper quota rule, rounding up a special quota to the nearest integer. We remove the decimal and add 1, regardless of what the decimal is. So here, we're going to take away the 0.6 and round up. That makes sense, right? Because 0.5 rule tells us to round up. But according to the upper quota rule, we actually do this here when it's less than 0.5. So when it's 0.2, we still take it away and round up. No decimal equals no change. If I have 108, it stays 108. Keep that in mind. Now the lower quota rule is the exact opposite, rounding down the standard quota to the nearest integer. So we're going to remove the decimal and round down. It doesn't matter if it's 0.5 or above. The same applies. No decimal, no change. So here, if we've got 0.6, we don't round that to 36, even though it rounds up normally using the 0.5 rule. We just round it down because this is the lower quota rule. So that should be 35. This will be 99, 16, no decimal, no change. This will still be 108. These are our special roundings of quota, and we have to use them in order to equal the total number of seats. So, example 3b, going back to the example we had before, let's find the upper and lower quotas of the 6, it says nations, but states, from example 3. So state A would go up to 33. Again, it doesn't matter. And I'll look at this and then I'll go back down and verify. Round every number up regardless. So 33, 138, 4, 42, 14, and 20. The problem there is I get 152. Let's round every one down. 32, 138, 3, 41, 13, and 19, as you can see. Now we've got 246. So if all the will the lower or upper quotas be equal? If all standard quotas are whole numbers, this will be true. This question goes back and just basically states, hey, is there an opportunity for the lower and upper quotas to be the same thing? The answer is yes, if you have no decimals, period. No decimals means that when you do the upper and lower quotas, they should equal the same thing because there's no rounding involved. Now, the apportionment method means that we will use some concept of upper and lower quotas to meet the exact total. Let's see what I mean here. For example 4, and we've only got 2 examples left. For example 4, it says the school board wants to assign 30 new teaching assistants among 5 elementary schools, based on the current number or enrollment of students in the schools. This is true, we do this. Complete the calculation for standard divisor and standard quota for the table given. So we've got these 5 elementary schools, north, south, east, west, and central, and here are the student numbers. So first of all, you need to find the total. Add 375, 297, 408, 340, and 380, and we get 1800. Well, we then use that 1800 to find the standard divisor. 1800 divided by 30. Why 30? 30 are the new teaching assignments that we are going to get. And that, if you go back up here, is the number of seats that we're allowed. 30 new teaching assignments. Okay, so 1800 divided by 30 equals 60. So what we're going to say here is there needs to be 60 students per 1 teaching assistant. That's the standard divisor that we have. Then what we're going to do is find the standard quota. Remember, we take the population of that state and divide it by the standard divisor. So 375 divided by 60 is 6.25. And again, we use that all the way through. If we were to then, well, it doesn't ask me. It just says complete the calculations for standard divisor, and standard quota. But we could then add those all together to see if we equal 30 new assignments or not. Okay, so make sure that you're looking through there. Doesn't ask me to do it, so I'm not going to do it. But if you did, to double check, you could. Let's look at example 5, because what we're going to do on example 5 is actually complete an entire table with the upper and the lower quotas. For example 5, it says there are 4 players with 200 seats. It kind of simplifies this down. You don't have to identify seats, players, or population. So for 4 players and 200 seats, complete the table by finding the standard divisor, standard quotas, and upper and lower quotas, and then round those using the standard quota as well. So you can see our populations. First thing to do is add them together. 125, 150, 350, and 275 to get 900. The standard divisor is going to be 900 divided by 200, which is 4.5. The standard quota, 27.7 repeating. Again, how did I get the standard quota? Population divided by the standard divisor. Where did I get this 200 for the standard divisor? That's the seats available. The 900 is the total population of all the states. So 125 divided by 4.5, 150 divided by 4.5, 350 divided by 4.5, and 275 divided by 4.5. Now we add those standard quotas together, and what we should get is the 200 seats that we have exact. What we're going to look at are the 3 quotas that we have: standard rounding or normal rounding, upper and lower quotas. Normal rounding is the 0.5 or above. So 27 goes to 28, 33 rounds down to 33, 77.7 repeating, up 61.1 repeating, stays at 61, round down. Adding those together gives us an exact 200. That's good. The upper quota, remove the decimal and round every number up. So this is going to be 28, 34, 78, and 62. When I add those totals, I get 202, which is over our total number of seats. The lower quota, remove the decimal, round down. 27, 33, 77, and 61. This gives me a number of 191 added together, which is under the total seats available. So we then have this definition called good apportionments. This produces a valid, or exactly the number of seats we were given, and a fair apportionment. So the good apportionment would be used in the normal rounding, the most fair that we have, the closest without going over, or exact. So in this case, it would be the normal rounding. Okay.